between the capacitor and the inductor. They both store energy as the charge moves back and forth between one plate of the capacitor and the other. But of course, and in that case, the energy is conserved because the only way that a circuit can dissipate energy is if it has a resistor. And if we did put a resistor in there, what we discussed is that obviously it oscillates, possibly if the resistance is not too large. When the resistance is too large, then it wants to oscillate, but it doesn't quite make it, and it stops before even spends all the energy before the first oscillation. That would be an overdamped oscillator. There's something called critical at a critical value. Obviously, is when you go from not oscillating at all to oscillating, and that we call critical damping. Right? That's the point where you go from oscillating to non-oscillating. So, but the point is that it dies out. So one way to keep it oscillating is to put a power supply that forces that oscillation on the circuit. All right? So this is called an AC power supply, an AC source. An AC is alternating current source, all right? And it's described by a sinusoidal function. Okay, so I chose a cosine that has a maximum voltage V0, and in that sense, this source will force that oscillator to continue to oscillate even if it wanted to die in the first place. And this we call a forced oscillator. And it also exists in a mechanical spring. If I have a spring and a mass and I force that to oscillate, it will continue to oscillate if I just push it, right? Let me see. So let's see the different types of oscillations that we could have. I didn't unfortunately bring a spring and a mass. It's complicated. I have to build one to bring one. But anyways, let's use our imagination. Thought experiment, as Einstein would say. I wish it was as complicated as what he had. But anyways, it's simple. Thought experiment. We have a spring and we have a mass. And we force the mass of the spring to oscillate by moving my hand up and down, right? If I start very slowly, the mass will basically follow my hand, right? So if I'm the cosine omega t function with a certain amplitude, but I do it at a low frequency, the mass will respond exactly like the source. Now if I start to move faster and faster, if you remember, if you've played with a slinky, all right, sometimes you see that you're moving your hand away from the slinky and the slinky is actually stretching out further away. So that's like the mass in the spring. So I start to oscillate, it starts to oscillate, and then it starts to go out of phase from my hand, out of phase, meaning this angle and the mass position are not longer in phase. Before they were in phase, right? Before the angle, my mass was moving like I was moving, so this phase angle was 0, so they were in phase. But as I start to move it faster, as omega starts to increase, suddenly you start to see that phase angle increase. At some point, in fact, the mass is going opposite. So if I'm going up, the mass is going down, right? At some point. And then if I do it super fast, like the mass is like, should I oscillate or not oscillate? It almost stands still that it's so fast, right? So you have these extremes. Initially, the mass seems to oscillate with my hand. At some point, it starts to be out of phase from my hand and oscillates quite largely. And then when it's super fast, the mass does, in fact, the oscillation is basically 0. The amplitude of the oscillation is nearly 0. It's so fast that it cannot respond to my hand moving so fast, right? So these are like, so you get an idea of how this will also work, all right? So if I start initially with a low frequency, the whole current will be like, everything will be in phase. But if I start to accelerate things in the current, probably, and the voltage will be not in phase anymore, right? The voltage pushing that current through will not be in phase with the current. But at a very, very, very fast frequency, maybe the current is as if there's just like, no, it's so fast that the current will stop. Let's look at this in detail. But before I go into that, now that I hope we have a picture of what this system will do, I have to teach you about the math that we're going to do to solve this problem. All right, we're going to use something called phasors. Can you talk louder? No. That would be cruel. I mean, really cruel. Did I give you that impression? Really? I didn't know that you had that impression of me. But anyways, now I know. Yes.
Are we going to be reviewing?
I can't hear you.
Are we going to be reviewing for the exam in the afternoon?
No. No. No, we have to finish this chapter by Friday, so there's no way. Hmm? All right. So the phasors are the math that we're going to be using to describe this, the RLC circuit or RL circuit, or I mean all the circuits that we just saw previously in chapter 30, but now with a source that will push the current through. All right. So a phasor is just simply a vector that doesn't change in magnitude, but it rotates in vector space where it has, and this is not officially what we're doing, but I can tell you that will be our solution to our problem. Okay, so this is not the word I'm going to use. Not because we're going to use it, but so that it starts to ring a bell when you are in your 200 level. Elements are exactly behaving in time.
So what about the vertical component?
That's the imaginary component. So later you're going to see this vector as a complex number that has a real and an imaginary component. And the math of the circuit in the complex plane becomes a very easy problem, and that's why we use complex numbers. But ultimately, the real solution to the circuit is given by the projection onto the real axis, onto the x-axis, okay? The characteristic of these phasor vectors is that they maintain their length. Their length is fixed. What's happening is that they're rotating at a certain frequency, omega, all right? And at any instant t, I just project this vector onto the x-axis and I get the real solution. You've seen this before, right? It was, again, a mass, a circular motion. We could represent the mass in a spring as if it's moving in a circular motion. And the projection on the x-axis gives you the solution of the spring in the x-axis, if you want to remember. But anyways, a phasor is a vector, all right, whose magnitude is not changing, but it's rotating in time. Its projection onto the x-axis or the real axis is a solution, all right? And we're going to put a bunch of these vectors that represent several things in the circuit. For example, this one represents the current, all right? All right. So now we can immediately see, let's build this circuit. Ultimately, we're going to get to the RLC circuit, but let's build each element at the same time. Okay, I mean, let's build one element at a time. So let's just first add a resistor connected to an AC source, and let's see how that responds. So the voltage is given by this function that I told you, which is basically connecting it out of the outlet of your wall, right? That's an AC source. Sorry. Volume. All right. So the voltage is an alternating source defined by this cosine omega t, and I have a phase to it. All right. So if I go around in Kirchhoff's world, right, using Kirchhoff's rules, which are covered in this exam, all right, you go from A to A, and you basically see that the voltage across the resistor has to be the current times the resistance, right? That V on the top is the voltage across the resistor, IR. Okay? Now, in this case, okay, as you can see, because the voltage equals also the maximum current times R, that has to be V0. And if the current is I cosine omega t, right? And I place it on the top, I realize that I times R must be V0, right? Now what about the angle? These must be in phase, all right? There's no reason, since I use, let's see, maybe I should write this down, right? We get, okay, voltage across, I go, Kirchhoff's rules, no? From A to A, gives me the voltage across the source, all right? Minus the voltage drop across the resistor must be equal to 0. The voltage across the source is V0 cosine omega t plus phi, all right? And I propose that the current, the voltage across the resistor, has to be equal to the resistance times the current. Now the current is an I as a function of t. So I propose that the current is not in phase initially with the voltage, right? The voltage source, the source voltage is V0 cosine of omega t plus phi. So I propose that the current not necessarily in phase, as we discussed. Potentially they don't have to be in phase, but it has an amplitude, and it's just simply rotating with time like this. So if I make this, I put these two solutions, this proposed forms into my Kirchhoff's equation, I get minus R I cosine omega t, right? Equals to 0. Or this is true, right? How are these two equal to each other? The only possible way that these are equal to each other is that V0 must be equal to IR, the maximum amplitude of the current. I could even put an I0 there, all right? Maximum current times R, and also if these two are to be equal, that means that the phase angle has to be 0 too. There's no other way that these two functions could be the same, unless phi was equal to 0. So in a circuit that only has a resistor and it has an AC current, the current, okay, and the voltage, so the current is described by this omega t, but the voltage source, the source of across the voltage is also along the current. So they are sort of, so that's the voltage phasor. I don't know. Yes. Why did I put R? I have to put S here. All right. This is the source, right? It has a voltage, and it's in phase with the current. And so this is the source, and the voltage has a different, obviously this is V and this is I. If I multiply I by R, then these two vectors must be the same length. And both vectors are equal to each other, and they're rotating omega at an angular frequency of omega. All right? So in this case, the current and the voltage that's pushing that current and the current flowing through this circuit are in phase. It's like my hand doing just simply this and the mass doing that. All right? Now in this case, as a function of frequency, it doesn't matter. It's not quite, the spring might not be the best way to describe the circuit, all right? It may be, it actually, the best description to this case would be a rod, a metal rod with a mass, right? The mass and the rod, no matter what I move in my hand, right? It will be always in phase with my hand, right? If instead of a spring I had a rod, the mass has no option but to follow my hand at every point. Do you agree? Yeah. Good. So that is the case for this case. No matter what the frequency is, my mass will always follow my hand if my hand is moving. This is the same in this case. If I only have a resistor, the voltage is pushing the current, and the current on the resistor, or the current of the circuit, will be in phase with that driving force called the voltage. All right? They're in phase, and the amplitude of the voltage simply equals the maximum current times R. Oh, look at that. Quick, so you get warm up and stop studying. No. A resistor is connected across an AC source as shown. For this circuit, what is the relationship between the instantaneous current I through the resistor and the instantaneous voltage AB across the resistor? It's simple, right?
Mm-hmm. V equals IR.
V equals IR, that's right. So I is maximum at the same time as the voltage across AB. Is it a quarter of a cycle off before, a cycle of a quarter after? Are they out of phase? That's what it means. 2 of A, B, and C are possible depending on the circumstances. All of the 3 A, B, C, D are A, B, and C are possible depending on the circumstances. So, what letter is it? What is the right answer?
A.
A. Right? Right now, for this circuit that only has a resistor, the voltage across the resistor is simply IR, and I is in phase with the voltage. So it's maximum when the voltage is maximum, it's minimum when the voltage is minimum, right? Okay, there's another thing that we need to look at. It's called the root mean square, and I mentioned it before, and I told you that we're going to see it later. All right, the root mean square value. All right, when you have oscillating functions like these, all right, and I tell you what is the mean value of this function, let's say the voltage, V0, all right? And I ask you, what is its mean average over one period of oscillation? What would you say it is? How do you calculate averages? You add all its values and then divide by the, in this case it's time, right? The period. So I'm going to start, right, for example, this one is easy. It starts here, at one oscillation means that it ends there, right? Goes down and then up. So I start adding all the values of this function from this point to that point and divide by this time, right? What does that give me? That's 0. That's why the average is not a good number, because the average is 0. So the way to get a sense of what is, you want to get a sense of the value of V0 by having some type of average, but it cannot be the actual average because that would be 0, all right? But I can do a trick. I can square this function first. If I square it now, the function becomes positive everywhere, right? I add it. Now I add all of the result of squaring that function, right? So let's say I have a cosine function. Okay, it starts at 1. Well, V0, right? And then it goes down like this, and like that, and like that. It doesn't matter where I start. Let's say that I start from here to here, and this is the period, right? This is the period of oscillation, right? And as we discussed, of course, my drawing is horrible, and that's why I have slides, because my drawing abilities are, like, not existent. But if I indeed add all this area and divide by t, I get a 0. So my trick will be to square this function, all right? So I'm going to square this function. So if I square this, of course, I get a big number over here. I get a 0 here, but I square this part, and of course, this becomes positive, right? And then I get to this point is 0 again, and this part is positive, like that. right? So again, in this region, now the function I have to add is always positive, right? So now I add all that, divide by the time, all right, and take the square root of that. And that's called the root mean square, okay? So you take the square, and then you do the mean of that squared function, and then you take the square root. And that way you will not get a 0. All right, so that's our trick. All right, so that in the mean is, as we said, is equal to 0. All right, if you have a, all right, I don't know why I have, anyways, I'll fix this. Okay, so we define the root mean square as you square the function first, then you take the mean and you divide by the period, and then you take the square root. For example, for the cosine function, all right, so you make that squared, all right, first. So taking the mean of this function means 1 over the period, the integral of cosine square omega t over the period from 0 to t. All right? The integral of cosine square omega t, I have to go back and doing trigonometric identities to make this an easy function to integrate. Turns out that the cosine omega t is cosine 2 omega t plus 1. All right? And here I put how I get it from this identity of cos squared theta minus sine squared theta equals the cosine of 2 times theta. All right? Now, this splits up into 2 integrals. One that integrates the cosine and one that integrates 1. You see it? The integral of this cosine omega t, or 2 omega t over the period, also gives you 0 for the same reasons that this is an oscillator. So this cancels, gives you a 0 from 0 to t, but what survives is this term, which is a t. Okay, so the integral of dt from 0 to t is t. All right? But you have a 1/2 here, so you get t over 2, so it gives you v0 over the square root of 2. So the RMS, the root mean square value of the voltage, when the voltage is described by a sinusoidal wave, is simply the maximum value of that voltage divided by the square root of 2. So if I tell you that the RMS value coming out of the wall is 120 volts, actually the maximum, all right, the maximum value is the square root of 2 times 120 volts. So that's actually the maximum voltage coming out of your outlet, all right? All right, now let's add another element to our circuit. Let's see what happens. Any questions here? So our sources are going to be now alternating, all right, described by sinusoidal waves that could have a phase relative to the current, all right? The current is like the mass that I was talking about, all right? And my hand is the source. So the source and the current may be out of phase, and that's represented by that phase angle that I wrote. We're going to describe the elements of the voltages across, or the currents across different elements of our circuit as vectors that we call phasors. The characteristic of these phasors is that their length doesn't change. They're just rotating on this phasor plane. If we want to know the instantaneous solution of what's going on in each one of these elements, like the voltages, we just project these vectors onto the x or real axis, and we get the solution. All right? So now let's complicate our circuit. And finally, the RMS value. The RMS value for any sinusoidal function is now the maximum value divided by the square root of 2. All right? Because the average is always 0, so it's a useless thing to do in a sinusoidal circuit. Okay, so now let's add an inductor. All right? All right. So now, because we have an inductor, we have to apply not Kirchhoff's laws. We're gonna have Faraday's law. But you're very familiar with this because that's exactly what you're going to be answering about, right? This evening. So the top corresponds to Faraday's law, and I go around the circuit, all right, from A to A, and I have the voltage across the source, all right, plus the current IR must be equal to the EMF produced, which is equal to minus the self-inductance dIdt. So I just simply rearrange these terms and put that the current will be I cos omega t, and the voltage will be V0 cos omega t plus a phase. Okay, so that's the proposed solution for my equation, and I substitute it into the equation, and I do get a solution. So that's the thing. I propose that the current is also oscillating with the same frequency as my source, but it could be out of phase from my source by an angle phi. So by using this as my current and this as my voltage, and I put it back into this equation, so here, here's the voltage. Now the current, I basically propose this, and I put it in here. I get an equation that has a solution if and only if, okay, the amplitude of the current that I propose that solution is related to the voltage like we would expect, V0 equals IR, but now there's this phase angle. Now there's this phase angle, all right? So this phase angle is related to a quantity we define, okay, as the inductive reactance. The inductive reactance is simply omega, the frequency, times L. All right, and it's in ohms. Let's see. These are the details of, so let's see if I put it in a phasor diagram, because it would be somewhat easier to, so these are all the details to solving that equation, and I don't want to completely cause you to collapse in sleep, so I'm not going to do the total details, but who doesn't have it clear what, I mean, the basic thing that I'm doing is I have an RL circuit with a source that is alternating. I solve Faraday's law for this circuit, which is the top line, and I say, well, the voltage is alternating, so it has to have a form of a maximum amplitude V0 cosine omega t plus a phase, because the current and the voltage may not be in phase. It may be like the previous one with just a resistor. They had to be always in phase. But now let's see if that's the case. For the current, I say is just simply I cos omega t. The frequency, however, the way the circuit responds has to be at the frequency that it's driven. They may be out of phase, but they cannot be different frequencies. So that's why I propose this as my solution. And if I put these two things in my resulting equation, okay, I get a solution with a certain relationship between the difference, like the amplitude and the phase, okay? So this is a relationship between the amplitudes of the voltage and the current and the phase. Whereas you can see the phase angle, how much right? This relationship gives me the phase angle, depends on the frequency. Psi L is the inductance reactance omega L. So it's omega L over R. The phase angle depends on the frequency. And we already had an intuition by using the spring and the mass. This thought experiment that we discussed at the beginning, right? If the frequency is low, right? This angle, the frequency is low, then, so this is nearly zero. So the angle is zero. So that means that they're in phase, right? As I increase the frequency, this angle starts to grow and grow and grow, and until they become completely out of phase, right? But then if you go back and make it super fast, all right, we have to do the math clearly, but basically, even though it looks like it's oscillating, eventually it basically sees, I'm going to plot it, oh, do I have it? The tan function, okay, becomes infinite or zero, and therefore it doesn't, again, it might be oscillating really fast, the angle may be going back and forth, but you will see that the amplitude, right, the current amplitude also depends on this phase. So Let's see.
You need to go back to that.
Yes. So the most important thing here is now the current and the voltage are going to be out of phase, and this phase angle will depend on the frequency. At the lowest frequency that you would expect them to be in phase, but as the frequency increases, okay, the phase angle increases. All right? Can I?
Yes.
All right. So this would be a plot of the current and the voltage. Okay, so the voltage angle. So a sine omega t I can rewrite as a cosine omega t plus pi over 2. All right, it's exactly the same thing. I just move the sine by a phase angle, or by a cosine by a phase angle, and I get a sine function. All right? So what is the voltage across? Okay, let me see. Let me see if I can. I'm going to follow Isaiah's suggestion going back one. All right? So going back to this equation, which comes from Faraday's law. The voltage of the source, the voltage across the resistor, the voltage across the inductor equals 0. Right? After I rearranged everything. Right? 3 terms. The source, the resistor, the inductor. The voltage across the inductor, the voltage across the resistor, the voltage source. The voltage across the inductor could be positive or negative depending whether the current is increasing or decreasing, remember? So this depends on the sign of di dt. Anyway, so if I put in my solution, I get these terms. So this is the voltage across the inductor. All right? Right? The cosine omega t. And I think this should have had, okay. All right. Here we go. Let's see. So this is the current, and this is the voltage across the inductor. So the current is a cosine omega t. The voltage across the inductor is a sine omega t because I had to differentiate the cosine. You see it? The voltage across the resistor is a cosine. The voltage across the inductor is a sine. So this is the description of the current on the circuit. This is the description of the voltage across the inductor. And you can see that the voltage across the inductor is out of phase from the current. By how much? By this angle pi over 2. 90. How do I describe this in a phasor diagram? Like this. I have a current, which is which if I multiply by R is the voltage across the resistor, right? Which is its projection onto the x-axis gives me the cosine omega t that I need. The voltage across the inductor, however, is 90 degrees out of phase from the current. So this would be the voltage across the inductor, 90 degrees ahead by this plus sign from the voltage across the resistor, or from the current. The voltage across the resistor, since it's only proportional to the current, that part, the voltage across the resistor is always proportional to the current. So they're always in phase. But the voltage across the inductor is across the resistor, right, from our equation. This voltage across the inductor. So, and therefore the voltage across the source has to be equal to the sum, right? So the equation, where is it? Yes, here. This is the voltage across the source, the voltage across the resistor, the voltage across the inductor. All right? So the voltage across the source, if I put them on this side of the equal sign, must be equal to the sum of the voltage across the resistor plus the voltage across the inductor. Yes? If I just rearrange these equations to put them over here so we can read them as the voltage across the source must be equal to the voltage across the resistor plus the voltage across the inductor. In phasor space, since these are vectors, what this means is that the voltage across the resistor plus the voltage across the inductor as vectors gives me the voltage across the source, which would be this vector. And its magnitude has to be equal to V0. Right? Now, because the inductor, the voltage across the inductor and the voltage across the resistor are proportional to the maximum current I, as long as I define this impedance, reactance of the inductor as omega L in ohms, R is in ohms, then I can also define the voltage source as having a current times another variable that depends on resistance, and that we call the impedance. And you being engineers, you probably heard of impedance. So impedance is the resistance for which we have to multiply I that gives me the voltage on the source, which is V0, or 170 volts out of the outlet. And then to finalize, let's ask a question. An inductor is connected across an AC source as shown. For this circuit, what is the relationship between the instantaneous current I through the inductor and the instantaneous voltage VAB across the inductor?
I is maximum 1/4 cycle after VAB.
Before or after?
I think after.
So think of this phasor diagram that I just, so there was the current. And the current is like this in the phasor diagram, right?
Mm.
So let's say that at a time t it's rotated this amount. So that's omega t, and that's the current, right?
Mm-hmm.
Of the circuit. Then we just learned that the inductor, the voltage across the inductor is 90 degrees, 90 degrees from the current. No, that's the voltage across the inductor. And that has to be 90 degrees.
Mm-hmm.
So is I max a quarter of a cycle? What's a quarter of a cycle? A full cycle will be 2 pi.
Mm-hmm.
A half a cycle?
But VL is 90 degrees ahead of I.
Yes, so I is relative to this one,
Mm.
behind.
So that
Right?
means I is maximum 1/4 cycle after VAB.
I is maximum 1/4 after, yes, after VAB, right?
Mm-hmm.
It's lagging behind. All right, a quarter of a cycle would be pi over 2. I know you're thinking about the exam, but if you instantaneously had something to do with this lecture today, which was heavy, okay? Do you have questions? No? Let me see if I have another problem. One more. Oh no, I don't have any more problems. Then we talk about the RC circuit this afternoon.